The forensic reconstruction of Hawker Typhoon Mk1B serial number RB396 begins with a documented operational anomaly. The return-to-flight project is anchored on a verified surviving structure, not on an assumption that wartime damage alone defines the engineering baseline. Over a 4-month operational window, frontline ground crews repaired flak damage on this specific airframe 18 separate times. This metric defines the low-altitude attrition cycle. By the final months of the war, RB396 was documented in low-level armed reconnaissance and ground attack work, rather than in the high-altitude role for which the Typhoon had first been conceived. In that envelope, it could face intense light anti-aircraft fire from concealed ground positions, roads, and vehicle columns. Surviving this environment required airframes capable of absorbing continuous kinetic strikes without catastrophic failure. The objective of the modern recovery project is to return this exact identity core to certified flight, a mission constrained by the extreme structural fatigue the aircraft endured during its wartime service. Built in November 1944, this aircraft entered the European theater as low-level strike missions reached maximum intensity. Its massive 24-cylinder engine, armored forward bulkhead, and heavy weapons fit made it a powerful but heavily stressed battlefield machine. At the altitudes required for armed reconnaissance and ground attack, each sortie imposed high aerodynamic loads, vibration, rapid maneuvering, and maintenance demands on the same structure. Flown predominantly by Canadian pilot officer Frank Johnson, the aircraft accumulated at least 35 documented combat sorties. Reaching this number of missions in a low-level ground attack role placed a heavy operational burden on a single airframe. Each mission increased the maintenance burden and gave ground crews new damage to assess. The record supports repeated flak repairs, but it does not securely identify every damaged system or prove a continuous fatigue history inside the main spar and ribs. Ground crews executed rapid field repairs that restored the aircraft to operational use when it was past fit. The low-altitude attrition cycle dictated a strict mathematical limit. Eventually, an aircraft would encounter a strike sequence that bypassed all armor and severed a primary flight control or power system. The operational limit for this specific airframe was reached on April 1, 1945. Flight Lieutenant Chris House took command of the Typhoon for an afternoon tactical strike. The objective was a concentration of mechanized enemy transports about 5 miles northeast of Hengelo in the Netherlands. House's low approach allowed visual identification and engagement, but it stripped away recovery margin if the complex engine failed or took damage. As the Typhoon attacked the transport column, rapid-fire light flak intersected its flight path, and the aircraft began losing height. The surviving summaries support a loss of power and a controlled forced landing more clearly than they support a detailed diagnosis of an independent loss of lift. House made the controlling procedural decision. He stayed with the damaged aircraft and committed to an immediate forced landing. He guided the damaged aircraft down near Denekamp, with later local research placing the crash site northwest of Denekamp on the Dutch-German border. The procedural decision to retain the aircraft in a controlled glide rather than attempting to jump at low level preserved his life. The aircraft struck the earth, skidding to a violent halt. House survived the massive kinetic deceleration, while the damaged structure remained embedded in the Dutch soil. The aircraft had endured a brutal operational life, but the final strike exceeded its design margins. What specific mechanical threshold forced the aircraft to the ground on April 1, 1945? The survival of the structural identity depends less on a proven crash mechanics model than on what physically remained after the forced landing and post-war recovery. The aircraft came down near Denekamp, and the rear fuselage later survived as the project's identity core. Public summaries do not reconstruct the exact energy path through the forward structure, but the known architecture matters. The Typhoon's forward section was a rigid, tubular framework carrying the power plant and armor, while the aft fuselage was a monocoque aluminum shell of skins, frames, and stringers. The safer conclusion is that much of the forward aircraft was lost, while the aft structure endured as a contiguous section. Following the impact sequence, the operational life of the aircraft officially ended. The pilot departed the immediate wreckage, beginning an evasion route that lasted 3 days before he successfully crossed back into Allied territory. The airframe remained stranded in the agricultural zone. Without military recovery assets deployed to retrieve it, the complete fighter plane sat exposed to the elements. As weather systems moved across the border region, the heavy structure settled deeper into the soft soil. When hostilities formally concluded later that year, the legal and operational status of the downed fighter shifted permanently. It transitioned from a stranded military asset to discarded battlefield debris, creating a new vulnerability. The European environment in late 1945 created a severe threat to any surviving forensic evidence. Local authorities operated under rigid economic constraints, prioritizing agricultural restoration and industrial reconstruction. Cleared land and raw metal held immense value, while historical preservation held zero priority. This economic reality initiated widespread post-war material liquidation. Systematic scrap drives swept across the rural borders, targeting thousands of wrecked aircraft, abandoned tanks, and disabled transport vehicles. Wreckage recovery teams approached the downed fighter to extract concentrated aluminum, copper, and steel for immediate industrial recycling. The public record does not preserve every tool mark, cutting sequence, or destination of each missing component. What can be said with confidence is that RB396 was recovered for scrap after hostilities, while the complete rear fuselage escaped the fate of the engine, wings, and forward structure. The dismantling created an unintended preservation boundary. As scrap teams worked backward along the fuselage, the metal yield dropped sharply. The rear section was thin, hollow, and far less valuable than the engine block or forward structure. The workers severed the airframe just behind the cockpit, and the lightweight aft shell moved into civilian use rather than industrial liquidation. That separation preserved the original geometry and rivet pattern assembled in 1944. The destruction of the forward aircraft was total, but the aft shell remained locked in a static state. How did a severed rear fuselage avoid total liquidation to establish a verified identity decades later? A severed cylinder of riveted aluminum skin possesses no complete aeronautical capability by itself. Yet in the heritage framework of this project, the surviving rear fuselage carries the verified identity of the combat aircraft. To reconstruct a certified fighter plane, the team must do two different things at once: preserve the historical provenance of RB396 and satisfy modern airworthiness requirements for every part that will fly. A highly accurate replica can be built, but it cannot honestly claim the same combat identity without a verified historical core. The surviving metal therefore anchors the story and identity of the project, while the civil flight approval must still be earned through engineering, inspection, documentation, and the permit to fly process. Tracing the physical custody of this surviving rear fuselage required documenting its movement across several decades. After the battlefield recovery, the section passed through a scrap dealer and then a chemical factory, where it was reportedly intended for a chemical wash use. Dutch enthusiasts then saved it for display in a small museum before it eventually returned to the United Kingdom. This localized chain protected the aluminum from total loss, but it also stripped the structure of much of its immediate military context. By the early 2010s, the rear fuselage had been identified as RB396 and returned to the United Kingdom. The project's own summary places that return in 2012, after which the section entered the HTPG collection. Moving the metal across the channel was a logistical achievement, but advancing from private storage to an active engineering rebuild created a larger administrative barrier. Returning an 80-year-old combat veteran to the sky was not a conventional restoration. It required certified aerospace engineering, precision manufacturing, major funding, and a governance model strong enough to protect the artifact from private sale, division, or financial collapse. In May 2016, the Hawker Typhoon Preservation Group was officially established under Charity No. 1167143. The charity owns and safeguards the project, coordinates fundraising, and keeps the rebuild aligned with its public memorial mission. Yet legal identity did not equal mechanical viability. Possessing the correct metal satisfied the heritage baseline, but the physical condition and geometry of the aluminum still dictated the engineering limits. Could the 80-year-old surviving structure serve as an airworthy baseline? To reconstruct an aircraft to modern airworthy standards, aerospace engineers rely on laser-calibrated rigid metal jigs. These heavy steel structures dictate absolute zero datum lines, ensuring every component aligns exactly to the mathematical blueprint. Inserting an original 1944 structural section into one of these precision modern environments presents a severe trade-off edge. If the engineering team forces the historical frame to fit the perfect modern tool, they risk inducing immediate stress fractures and destroying the artifact. If they do not use a rigid jig, the aircraft cannot achieve the strict structural symmetry required for civil flight certification. The clearest confirmed example belongs to the later tail rebuild. Original Typhoon tail components were effectively hand-built, and a trial fit in the inherited jig showed that the tail plane fixing points and rudder post alignment needed adjustment. The engineering team modified the tail jig so the assembly could sit squarely and securely before rebuild work continued. While the rear fuselage secured the legal identity of the aircraft, return to flight also required a viable Napier Sabre power plant. The original engine type was an exceptionally complex 24-cylinder sleeve valve design, so any wartime or unknown condition block would need extensive inspection, repair, and approved overhaul before it could be considered for flight. The project therefore needed an engine whose history, material condition, and rebuild path could survive modern scrutiny. To reduce this power plant risk, the recovery team secured a Napier Sabre 2A aero engine, serial number 2484 from Cranfield University. The project states that this example is believed to have been used only as a teaching aid, making it a strong candidate for assessment and rebuild rather than proof of automatic certification. With the engine risk reduced and the jig strategy clarified, the focus could shift back to the artifact itself. How is original, fragile material extracted without destroying the historic baseline? Extracting original material from an 80-year-old combat airframe introduces a severe material handling hazard. The inherited static state of the aft fuselage presented a rigid structural problem. The original skins carried exceptional historical value, including surviving second tactical Air Force paint and crash damage. But the airworthy rebuild required the engineering team to separate reusable frames and stringers from skin panels that could not simply be treated as flight-ready structure. The mandate was to retain as much original material as possible while accepting that some external and damaged material would be conserved as evidence rather than flown. The primary extraction barrier is the original fastening system and the fragility of aged light alloy structure. Thousands of countersunk rivets held the skins, frames, and stringers together, and each one had to be removed without enlarging the original holes or distorting the surrounding metal. Applying uncontrolled force to punch, chisel, or pry the fasteners out could damage the thin webbing and flanges that the project was trying to save. If an internal frame or stringer warped or cracked during extraction, that component could lose its value for reuse in the airworthy rebuild. To bypass this limit, technicians treated each fastener as an individual extraction problem. Specialized cutting tools were used to center drill the rivet heads, removing only enough material to collapse the clamping force. The corroded skins were then separated from the internal frames and stringers without lateral prying, allowing the team to strip away unusable outer material while isolating the reusable internal architecture. The pace was dictated by the fragility of the historic alloy. Once the external skin is fully removed, the surviving structural frames enter a critical assessment and conservation phase. Exposing the internal structures reveals decades of surface oxidation, localized pitting, and potential hidden combat stress. The engineering team must evaluate every extracted rib against rigid modern civil aviation standards. They conduct meticulous visual and non-destructive inspections on the bare aluminum. They must measure the exact depth of any corrosion to determine if the material thickness drops the frame below its required load-bearing capacity. Technicians specifically search for microscopic stress fractures, originating from the extreme operational vibrations of wartime flight or the deceleration of the 1945 belly landing. If a frame fails this inspection, it cannot be flown and must be replaced with newly manufactured metal. The operational trade-off forces the team to maximize the retention of original material while absolutely guaranteeing structural safety. Frames that pass this strict structural threshold proceed directly into active stabilization. The team neutralizes the active surface corrosion using highly controlled chemical washes, permanently halting the degradation cycle. This chemical stabilization ensures the 80-year-old metal will not continue to decay once sealed inside a new airframe. Following the neutralization process, the naked aluminum is coated in modern aerospace-grade primers. This modern chemical barrier isolates the historic alloy from atmospheric moisture, securing its physical integrity for future flight operations. With the internal components stabilized and protected, the work could move from conservation into structural assembly. Could the completed rear fuselage meet the standards required for return to flight? On October 30, 2024, the engineering team at Airframe Assemblies reached a definitive structural milestone. The technicians drove the final aviation-grade rivets into the rear fuselage section of the aircraft. By mating newly formed aluminum outer skins to retained and restored historical frames and stringers, the team finalized the first major physical phase of the reconstruction. This event marked a rigid procedural transition. The aft structure was no longer merely a collection of isolated, fragile artifact components requiring continuous forensic handling. It had become the first major airworthy standard section delivered for the return to flight project, while the complete aircraft still remained subject to further construction, inspection, and eventual approval. Achieving this physical milestone validated the preservation group's living heritage standard. Under that mandate, the leadership rejected a static museum outcome, where visual completeness can be achieved without full flight capability. The rear fuselage milestone mattered because the aircraft was being rebuilt not as a display shell, but as a future flying memorial. This unrelenting engineering standard was not selected arbitrarily. It is directly tethered to a precise memorial figure. During the intense low-level tactical ground support operations over Europe, the aircraft type suffered immense losses. The project records that 666 Typhoon pilots were lost on operations or killed while flying Typhoons during the Second World War. This metric drives the organizational objective. A static display cannot physically convey the intense mechanical noise, the complex operational envelope, and the raw kinetic energy of the aircraft these pilots operated. Only a certified, functioning airframe generating thrust and aerodynamic lift again can serve as a living memorial to the extreme operational environment those 666 individuals faced. With the aft monocoque assembled and the treated frames locked into the new structure, the engineering focus moved to the next funded work. Tail and tailplane structures, followed later by the cockpit, forward structure, wings, systems, and engine installation, needed to turn a completed rear fuselage into a complete aircraft. The technical roadmap remains strictly defined. The project can now work from a stronger rear fuselage foundation, but the remaining assembly is not a standard manufacturing sequence. Missing or partial information, obsolete British material specifications, corrosion control, jig modification, engine integration, and certification paperwork still define the route ahead. That completed rear fuselage gives the project a measurable restoration legacy. Hawker Typhoon RB396 remains the only verified combat veteran airframe of its type, actively advancing toward a return to flight. The active memorial objective will be achieved only when the remaining structures are built. The integrated aircraft satisfies the required approval process, and the verified identity of a tactical ground support fighter begins its first certified takeoff sequence. Geared directly into the operational airspace.